Welcome to the Explainer, everyone. We're jumping right in today because we are embarking on a pretty mind-bending journey. It's one that connects the green grass of your everyday backyard straight out into the dark vacuum of deep space. We're going to look at one specific number that silently dictates the rhythm of our entire world. So, let's start with a simple question. Why do we actually have seasons? If you ask around, most folks might tell you it's because Earth gets closer to the sun during the summer and further away in the winter. Well, I am here to tell you that is absolutely 100% false. No way. Our seasons have literally nothing to do with our changing distance from the sun. Instead, they are completely governed by a very specific invisible geometric angle. Section 1. Meet the axial tilt, our world's engine. 23.44 degrees. Seriously, burn this number into your memory because it is the absolute VIP of this explainer. This single geometric ripple effect is the master controller of our environment. I mean, it dictates the local daylight hitting your window right now, and it simultaneously controls how engineers pilot multi-million-dollar satellites orbiting high above our heads. It's basically the defining angle of our existence on this planet. Now, astronomers have a really fancy, complex-sounding term for this, the obliquity of the ecliptic. Let's break that jargon down so it's crystal clear. It is simply the angle between Earth's equatorial plane and its orbital plane around the sun, which we call the ecliptic plane. Or actually, if it's easier to visualize, you can think of it as the angle between Earth's rotation axis and a straight vertical line pointing directly up from that orbital track. But hey, don't let the technical definitions intimidate you. At its core, it's just the simple reality of that 23.44-degree tilt we just talked about. Earth doesn't spin perfectly straight up and down. It leans. Now, what's really interesting here is that this 23.44-degree tilt isn't permanent. Our planet actually wobbles. Thanks to the steady gravitational pulls from our moon and neighboring planets, this tilt slowly shifts over a vast 41,000-year cosmic cycle. It rocks back and forth from a minimum tilt of 22.1 degrees to a maximum of 24.5 degrees. Currently, in our little era of human history, we're sitting right in the middle at that magic 23.44 degrees. Section 2. The engine of the seasons. How tilt changes weather. Because Earth's rotation axis is tilted, our relationship with the sun changes dramatically as we make our yearly orbit. During the northern hemisphere summer, the North Pole tilts directly toward the sun. That geometric lean gives us longer days and much more direct, concentrated sunlight. Fast forward 6 months to the northern hemisphere winter, and that exact same pole is tilting away from the sun, resulting in shorter days and much less direct light. So the crucial takeaway here is this. Without this specific 23.44-degree tilt, those beautiful seasonal variations we rely on, spring blossoms, summer heat, autumn leaves, and winter snow, would basically vanish entirely. Section 3. Daylight around the globe. Tilt and geography. Let's ground this abstract geometry in some real human experiences. Look at how dramatically life shifts depending on where you are relative to that tilt. If you live at the equator, well, the tilt barely affects you. You get a very steady 12 hours of daylight and 12 hours of night year-round. But travel down to Canberra, Australia, at roughly 35 degrees south, and the tilt creates a noticeable swing, about 15 hours of daylight in the summer and only 9 in the winter. And at the extremes, the polar regions experience the midnight sun, where it literally never sets in summer, and the polar night, where the sun doesn't rise at all in winter. All of this dramatic variation is just because of 23.44 degrees. Section 4. Guiding satellites in space. Tilt in space engineering. Okay, let's pivot and see how this builds from sunny days on Earth to the high-stakes world of spacecraft engineering. To put something into space and keep it fully operational, you need to know exactly where it is at all times. Space engineers rely on two fundamental celestial coordinate systems. First, there's the equatorial coordinate system, which is based on Earth's equator and uses terms you might have heard of, like right ascension and declination. Then there's the ecliptic coordinate system, based on Earth's orbital plane, using ecliptic longitude and latitude. When you need to mathematically connect or convert between these two massive mapping systems, what do? Yep, you guessed it. You have to rotate your entire mathematical model by our magic number, the obliquity angle of 23.44 degrees. Understanding the sun's position relative to Earth isn't just fun astronomy trivia. It is life or death for a satellite. Engineers have to manage a sheer volume of critical operations based on this tilt. Just look at this rapid-fire list. They must calculate sun illumination geometry, perfectly predict eclipses so a satellite doesn't lose power, conduct thermal analysis to keep the spacecraft from freezing or frying in orbit, precisely orient solar panels to catch rays, calibrate Earth observation imaging, and handle the whole shebang of overall mission planning. Every single one of these operations relies entirely on understanding the obliquity of the ecliptic. Section 5. The Math of Solar Declination, Predicting Sun Position. Okay, stick with me here. I know this algebra looks a little heavy, but keep your focus on the big picture. This is the equation for solar declination. Essentially, how engineers mathematically predict where the sun appears in the sky on any given day of the year, represented here by the letter N. Notice what sits right there at the very front of the equation, multiplying everything else, our old friend 23.44 degrees. This math is practically the engineering cheat code, powered directly by our tilt. It's the exact formula widely used for satellite power analysis, remote sensing, and even solar energy calculations right here on Earth. And this brilliantly illustrates how this one single geometric parameter governs the intricate relationship between Earth, the Sun, and everything we launch into the celestial sphere. Whether we're talking about complex orbital mechanics, determining a satellite's precise attitude in a vacuum, converting between Earth-centered inertial frames and sun-related frames, managing spacecraft power systems, or even navigating deep space probes millions of miles away, it all traces back to the obliquity of the ecliptic. It really is just amazing to think about. We've gone from the reason leaves change color in your backyard to the hardcore mathematical formulas guiding probes through the solar system, all connected by one single angle. So, the next time you step outside to feel the warmth of the summer sun on your face, or you pull up a map on your phone that relies on a satellite GPS signal pinging from space, I want you to pause. Ask yourself, how does a simple 23.44-degree tilt make absolutely all of it possible? Thank you for joining me for this explainer. Keep asking questions, keep looking up, and I'll catch you next time.